All right. The last part of chapter 2 is looking at the quadratic formula to solve quadratic equations. So if we have the quadratic equation ax squared plus bx plus c equals 0 written in standard form, this will be your solutions to that quadratic equation. So we just substitute, we use the a here, the b in these locations, also a here, and then the c here. So if we look at this, we can see from the last video where this solution to the quadratic equation came from. Because again, if we normalize the problem by dividing by a, where the other one was the a would be 1 after you divided by, we can see the minus b over 2 term. And again, if we factored everything out. So going a little bit step further, we can come up with the general way of solving a quadratic equation. And at least, again, this is for real numbers. So this is the result of working through a little bit further of completing the square. And in this case, we don't have to divide by 1. You could, and then just the new terms would just scale by whatever that division is, and then you could still use this equation. But right now we can use the solution when a does not equal 0. So when a equals 0, the first term goes away and we would just have the linear equation, which is what we covered in chapter 1. And then this part ensures that we will have real numbers, not imaginary numbers. So these will be the cases. And again, in this chapter, that's what we'll be looking at. Okay, so we talked about in our previous class where we'll use the solution to the quadratic equation. This is projectile motion. And essentially, projectile motion is another kinematics problem, but again, we're moving in the x and the y direction. And so what we get when we look at projectile motion, if you throw something, it'll follow the path, or if you kick something, it'll follow the path of a parabola. So what we would have is if you give something an initial velocity at height 0 and you give it an initial starting angle, you can calculate its path along a line. Again, with this approximation, is we're ignoring air resistance, curvature of the Earth, rotation of the Earth, and the acceleration of gravity is constant over the range of motion, which these are pretty fairly reasonable assumptions. Again, over short distances, these would be fairly reasonable. So now what we can look at is define a starting velocity, a starting angle. This maximum height we're going to call h, and then the range that it'll move in the x direction we'll call r. So those would be the variables that we would have for projectile motion following a parabolic pathway. And again, this kicking a soccer ball would be the actual projectile. So again, soccer ball is the projectile. The red dot here is the point of projection. We give it an initial velocity at an initial angle. The pathway is the trajectory. H, capital H, is the maximum height. The total range, or the total x direction, here is capital R. And then the entire time that the projectile is in the air, we're going to call that capital T, and we're going to call that time of flight. Okay, let's work on an example problem using the quadratic equation to solve this projectile motion problem where somebody is jumping off of a diving board. So again, in this class, you'll be given the problem statement, a sketch of how to sketch it, and then the equation. In your later classes, you will learn how to take the word problems, create your diagram, and then figure out which mathematical equation to use to come up with the desired results. All right, so the first one, find the time in seconds when the diver hits the water, solve the quadratic equation. So when the diver hits the water, they will be at a height of 0. So now looking at our equation, we'll have negative 4.905, and we're looking for time, and that is our variable t squared plus 0.981 t plus 2, and again the height, this value here, will be equal to 0. So you can just use your straightforward quadratic equation. Another possibility is you could divide everything by the current A term, which is the negative 4.905, and then just rewrite it. So if we divide the entire equation, both sides, by negative 4.905, we end up getting t squared minus 0.2t minus 0.4078, and that would equal 0. So we divide every term, and then the right-hand side as well. 0 divided by negative 4.905 would still be 0. So in this case, we have A equals 1, B equals negative 0.2, and C equals negative 0.4078. Quadratic equation, T is going to equal minus B plus or minus the square root of B squared minus 4AC, everything divided by 2A. All right, so if we substitute our numbers in, we get 0.2 plus or minus the square root, 0.2 squared, minus 4, A is 1, and C is a negative 0.4078, and everything divided by 2 times 1. So again, just be careful here. We have a negative and then also another negative. So when you're entering the values in your calculator, just be careful, or you can just know ahead of time a negative times negative will be a positive, so you'll be adding that to the 0.2 squared. So reducing this down, you will get 0.2 plus or minus, combining the terms in the square root, we get 1.671 divided by 2. So remember 0.2 plus the square root of 1.671 divided on that whole thing divided by 2, and then 0.2 minus the square root of 1.671, that whole quantity divided by 2 will be your two different solutions. So substituting those values and solving, we'll get one of the x's to be equal to 0.746, and the other x, we would get negative 0.546. And these would be in seconds. So remembering, this is very similar to when we had the capacitor problem last class. We know we could not have negative capacitance, so in a similar sense, we can't have negative time. But again, this, you can think of this abstractly. If this was just a parabolic motion moving around and around, that would be for this person, if they were continuing on the path, they would have continued back here, and it would take 0.54 seconds to go back if they had that starting velocity to get back to the ground, because you can get to the ground if you continued it backwards the other way, but that's not physical to the way the problem has been defined. So we ignore the negative result. And again, this should be t, not x. Because that is the variable we're solving for. So the time required is 0.746 seconds. Find the maximum height of the diver if it is known to occur at 0.1 seconds. So this is our capital H, and we're given the time that we would have. So this whole equation here is the result for H. So now, to solve this problem, we just look at H at 0.1 seconds. And that is the maximum height, so we know that will be capital H. And everywhere there's a T, we put in 0.1. So going back to our original equation, we have the negative 4.905 times by 0.1 squared plus 0.981 times 0.1 plus 2. So when we enter all of this into our calculator, we should get 2.05 meters. That is the maximum height that the diver will reach. And again, if we look at it, it'll be at this point right here. The last part that we'll come up with is to use the parts of A and B to come up with a picture or a sketch of those results. So we're just got to come up with a graph for this problem. So we already know what our times and our time value is 0 seconds. If we plug 0 in for t, we know we have a height of 2. We calculated it with 0.1 would be our maximum, is 2.05. And then when we knew the height was 0, we had 0.746. So if we just plot this as a graph, and if we look at this as height versus t, we know if we start out at 2, and if we say that this is 0, we know that this point right here is 2.05. We know that that is going to occur at 0.1, and then we know that this point over here is 0.746. Therefore, we've answered the problem. All right, to summarize the chapter, we looked at 3 different ways of solving quadratic equations: factoring, completing the square, and using the quadratic formula. And we learned how to solve that or apply it to projectile motion. And the last part is the max or the min is halfway between the 0 values. So if we go back to this problem, this will be, if we continue this back, the maximum would be at 0.1, halfway between. Again, if we carried that back to our negative value that we would have had for the other 0.